everybody. Today we'll be talking about the graphs of product formation for enzyme-catalyzed reactions with the presence of an uncompetitive inhibitor. Here are the past graphs that have the product concentration based on changing substrate concentration for the non-inhibitor enzyme-catalyzed reaction, the competitive inhibitor enzyme-catalyzed reaction, and finally the non-competitive inhibitor enzyme-catalyzed reaction. Now, I will be doing a little bit of an overview again for uncompetitive inhibition, just because this specific inhibition type isn't often taught within general biology curriculums. Uncompetitive inhibition is when one or more of the substrates must bind to the enzyme before the inhibitor can bind. This means that two complexes could be formed, the ES complex and the ESI complex. Remember, the ES complex is the enzyme substrate complex and the ESI complex is the enzyme substrate inhibitor complex. But because the substrates must bind to the enzyme before the inhibitor can bind, the ES complex must be formed before the ESI complex forms. If the ES complex does not have the I bind to it, then it can proceed to have the product formed. However, if the inhibitor binds to the ES complex, this means that the product cannot be formed unless the inhibitor is released or dissociates from the ESI complex and returns to the ES complex. Similar to past videos, we will be qualitatively visualizing the process of adding more substrate to an enzyme-catalyzed reaction with an uncompetitive inhibitor. We will imagine a scenario with two main requirements. First, there is a constant concentration of inhibitors and a constant concentration of enzymes, while the only variable is a substrate concentration. This is because, again, the substrate concentration is our independent variable, and we want the concentration of inhibitors and enzymes to be controls. Second, the concentration of the inhibitor present doesn't saturate all the enzymes. So this slide is just an example of how an uncompetitive inhibitor will bind to an enzyme only after the substrate binds. As you can see, the inhibitor that was bound to the ES complex has the stars around it. This means that this specific ESI complex does not produce product, while the other ES complexes do. We will first show a situation with a lower concentration of substrate. With a low concentration of substrates, most of the substrates will bind to all the free enzymes. But after the substrates bind, because of the nature of uncompetitive inhibitors, the inhibitors will be able to bind to the ES complex to form an ESI complex and prevent product formation. This means compared to the other graphs at this point, the uncompetitive inhibitor will have a very slow initial rate of product formation because the inhibitors will nearly limit all of the substrates that are present and bound to the enzyme. Now we'll increase the substrate concentration. As you can see, the enzymes are saturated with the substrates. However, again, the inhibitors will be able to bind to the ES complex and prevent the product formation. Because we have a set concentration of inhibitors, though they didn't saturate all the enzymes available, we can begin to observe that the rate of product formation will start to become constant and thus lead to the maximum velocity, or the graph will begin to plateau. Finally, when we add a large concentration of the substrate, we can continue to see the constant maximum velocity of product formation and observe the consistent rate of product concentration. When we plot this reaction and compare the differences between non-inhibition, competitive inhibition, non-competitive inhibition, and uncompetitive inhibition, the uncompetitive inhibitor graph has the least steep increase in the rate of product formation. Furthermore, the plateau occurs slower than the non-competitive inhibitor, but faster than the non-inhibitor graph and the competitive inhibitor graph. This means that the uncompetitive inhibitor reaches the Vmax more quickly than the non-inhibitor graph and the competitive inhibitor graph, but reaches it more slowly than the non-competitive inhibitor graph. While we have qualitatively described how we would characterize the graph and extrapolated these qualitative assumptions to a general graph shape, we really need to begin to try and find a mathematical basis for these graphs. So we will begin to first discuss the concepts of equilibrium and law of mass action in the next video, which will help solidify some chemical and mathematical basis for proving our graphical assumptions. Thank you, and we hope to see you in the next video.